All right, so you've watched the videos on AP Classroom, and what you should know is as follows, that if we have going from lower to a higher index of refraction, that you're going to get a half a phase change, half a phase shift, okay? And then if you're going from higher to lower, you're going to get a full phase change, phase shift, okay? Which means you're really getting no shift at all. All right, we then looked at thin film interference and what's happening, what the thin film equations are. All right, thin film equations for one layer of film, that's like oil sitting on top of water, where you're going from lower to higher to lower again. So this would be like air, where N is 1, oil, where N is 1.4, and water, where N is 1.33. So if we're going from lower to higher to lower, you get one film. This is what happens. So you have two different equations. You have one for constructive and one for destructive. All right, the one for constructive interference is 2dN. All right, the N comes from, I'll show you in a second, equals M plus 1/2 times lambda. The N comes from, this is lambda in the medium. This is the medium. So if we want lambda from the medium, then that is, remember when we did the original, when they did, AP did the original formula, their lambda was in a vacuum, was in the air. So to get lambda from the medium, if you remember, N for the medium is equal to lambda in the vacuum divided by lambda in the medium, whatever it's going to be. So lambda in the medium is going to be wavelength in the vacuum divided by N. So which is really what we're getting. All right, so if we have a wavelength, that's what we know. All right. So now, destructive is going to be 2dN equals M lambda, okay? So now we know the path difference is 2D. This is coming from, of course, because it travels, some of that light travels twice. It travels D, basically it travels D down through here and then back again. So 2D is the wavelength path before it bounces off and comes out. So that's its difference, its path difference between the light that comes through, refracts, comes back, reflects off of this layer and comes back through with no phase change. Then this stuff that comes in and bounces off. So the difference between this path and, maybe I should do this way, between this path versus, say, this path, once it gets to there, would be 2D, all right? It's traveled 2D further than the original reflected light has. So that's where the 2D comes from, the path length. All right, so knowing these two things, let's look at this. We've got a refractive index of oil floating on a puddle of water. So this is really the guy, this is our N, having a refractive index of water, having a refractive index of 1.33. The only thing we know about that is we know that it's one layer. We really treat it as one phase shift, not two, because it's going from lower to higher to lower again. Has an orange color corresponding to a wavelength of 575 nanometers, okay? So what we know is the wavelength here of the orange light. It says calculate the thickness of the film in the orange region. Okay, so what are we doing here? We're really taking this, we're using, because its color is corresponding to a wavelength, that means it's showing up, which means it must be constructive. Possible thicknesses of the film, we're going to start at m equals 0. So we're going to use 2dn equals m plus 1/2 over lambda. So we've got 2d times n, which is 1.4, 0 plus 1/2 times the wavelength, which is 575 times 10 to the negative 9th. If we solve for d, we get 1.03 times 10 to the negative 7th meters, which is approximately 103 nanometers thick. Okay, now that would be the thinnest it could be. Now it could be multiples of that too. Instead of 0, we could have 1, 2, 3 for m, etc. And those would also cause this same type of thing to happen. All right, so here we go. We have 2 layers this time. If you'll notice, the difference is it's going from lower to higher again. So we consider this 2 layers and then to something else. So this is 2 layers. What we find out with 2 layers is that the formula is reverse. So now we have constructive is two dn equals m lambda, and destructive is 2dn m plus 1/2 lambda. Okay, think about it. If it's going through 2 more layers, then it's going phase shift here, won't phase shift here, well, will phase shift again here, won't phase shift here. So you've got phase shift here, but not here. So you've got 2 sets of phase shifts coming on, which is the equivalent to reversing it. All right, so if they both phase shift, that's like not being out of phase together, and then you've got one. So depending on how long the wavelength of the light is, it's going to change what actually, how it bends, and which colors are destructive and which colors are constructive interference. All right, so let's look at our problem. Solar cell coated to ensures little possible light falling on the reflected, minimum thickness. So it's got, the solar cell has a high index of refraction, but the coating is really what we're interested in, which is 1.5. So we have an N of 1.5. Minimum thickness, which would mean M equals 0, wouldn't it? Minimize reflection of the light wave, so now we have lambda equals 524 nanometers. So this time we want a minimum. What do we want to know? Minimizing reflection also means it is going to be destructive. So we're again using 2dn equals m plus 1/2 times lambda. Let's fill everything in except d. 2d times 1.5, 0 plus 1/2 again, times 524 times 10 to the negative 9th. All right, so d ends up being, this time, d ends up being about 8.7 times 10 to the negative 8 meters, which is approximately 87 nanometers thickness. Okay? If you did not watch the videos, you're not going to understand what in the world I'm talking about and why. You'll have the doggone formulas, but this won't help you with anything. Okay? So make sure you go through and you watch the videos so you understand what's happening and why, and then do your homework. Okay? You need to do 6.5 and 6.6 homework.